Hi, everybody. Welcome, everyone, to the Computational Sustainability Virtual Seminar Series. This virtual seminar series is being organized by CompSysNet with support from the National Science Foundation and Cornell University. My name is Carla Gomes, and I'm the director of CompSysNet. Unfortunately, Doug, who normally hosts the seminar, could not make it. Doug, we hope you feel better soon. During the webinar, you can ask questions to the question and answer facility on Zoom. If you have questions to ask during the presentation itself, then you can also use the hand raise mechanism to ask those, and when convenient, we will promote you to panelists to ask the question aloud. We do encourage participation, and please do raise questions if you have questions. You can also use the chat option. If you have difficulties with today's seminar, make sure that you contact us and we will set up a test run for your node before future seminars. CompSysNet has several social media outlets, including Facebook, Twitter, LinkedIn, and CompSysNet blog. So please check all these options. So it's wonderful to have you here, and it's my pleasure to introduce today's speaker, Warren Powell. Warren is a professor in the Department of Operations Research and Financial Engineering at Princeton University and co-founder and director of the Laboratory for Computational Stochastic Optimization and Learning. Warren asked me to keep the intro very brief, so without further ado, Warren is going to talk about the unified framework for handling decisions and uncertainty. So yours, Warren.
Great. Okay, I think we practiced this, and so hopefully okay. Does everybody see the screen?
Yeah.
That looks good. Okay, great. I'm going to go fairly quickly. So if you like to do work on decisions under uncertainty, you love working on energy problems. Wind and solar have gotten a lot of attention. This is a year's worth of wind. It's highly volatile. It varies quite quickly. People do try to do forecasting. It's not very good. If you want to do solar energy, solar is a great form of variability because if you look at it over a whole year, you see the predictable changes in seasons, but clearly there's a lot of different types of variability. If you zoom in at the level of a week, we see predictable patterns of the sun rising and setting, and the very unpredictable patterns of the clouds, some of which are somewhat predictable. A very cloudy day, we can usually predict a day in advance. And then there's those spotted cloudy days where we don't even know what's going to happen an hour from now. This is a number of profiles within the day, and you can see the types of patterns. If it's a very cloudy day, we probably knew that yesterday, but when you have a sunnier day with jumps, I really can't predict that even an hour in advance. These are electricity prices. A lot of our energy problems involve trying to make money. We have to deal with these very, very volatile prices. The average here is $22 per megawatt hour. There's the average. And yet you see these spikes that are easily 10 to sometimes 30 times bigger than that, including negative spikes. So this is both a source of risk for people who have to pay these, but also an opportunity for people who want to use, say, batteries to store electricity or store energy when the prices are low and sell it back when it's high. Brazil, we're starting a project with Brazil. That's also a very unpredictable event as well. Brazil has had to deal with extreme drought. Rainfall is a very complex stochastic process because it has to deal with meteorological changes. The time scales are completely different than wind and solar. Brazil has large reservoirs to help smooth through this. Sometimes even those aren't big enough. We can also have uncertainty in terms of how the market may respond to price signals. If I want to discourage usage during periods where the wind is down or the sun has gone behind a cloud, but we don't know this response curve, there's a lot of uncertainty in this. So this is a type of structural uncertainty. There's really almost no limit to how many different types of uncertainty happen in these energy settings. So it's a great way to sort of extend your knowledge You do have to always be sure that you're distinguishing between predictable variability, such as the pattern of loads or the sun setting, with the different types of unpredictable or stochastic uncertainty that requires that you work on different timescales. So all of these problems, if we want to do analytics, if we want to use our tools of computer science, or I like to call them operations research, the first thing that you have to do is model them. And you have to take the physical problem and translate it to mathematics so that we can put it on the computer. Now, if you come from operations research, everybody speaks this language of linear programming. Universally, around the world, if you get a paper, whether it's from US or Europe or China, if it involves math programming, it's going to be done with this notation. Now, there is a large community that works in optimal control, and their notation is slightly different, but this is also fairly universal. So if you come more from an engineering community, you might write it like this. This is not quite as standardized, but pretty much. There's a number of books, and this is widely used. So here's the hard part. What happens when we put uncertainty into these models? Because all of this is deterministic. This is where things get very complicated. And over a career of running around trying to solve these problems, I've come to call this world the jungle of stochastic optimization. And if you try to put uncertainty in these things, you might end up working with any one of these terms, and behind every one of these terms is a book, possibly several books. Okay, so these are 15 of, I'll call them the major books, but some of them have close cousins. Some of these you are clearly derivative from another. The reinforcement learning book, very well known in computer science, draws its notation from that blue book on Markov decision processes. Yet the problem settings are different. Introduction to Stochastic Program, the upper left-hand corner, comes from the mathematics of deterministic math programming. Each of these tends to be motivated by a class of problems coming from a community that may invent all of its own notation on its own, such as the optimal control book, or sometimes it's derivative, where they'll draw the mathematical language from another community, which is what happened in the reinforcement learning community. They drew the mathematics of Markov decision processes, and yet the fields are quite distinctly different. The thing is, you can easily spend entire careers or major parts of careers in any one of these books, and you will emerge with a particular language for modeling problems and a particular class of techniques that will work on a class of problems. I don't want to say all these books are wrong. I'd like to say all these books are right. The difficulty is, as we learn to speak all these different languages, we actually end up learning to solve very narrow classes of problems. And I'm going to later make the case that that's very dangerous, because quite often you really do need to draw from all of these books. So I'm going to start off by walking through the elements of a dynamic model. One of the things that you will not find, so in a deterministic model, everybody writes these deterministic math programs a certain way. When you put uncertainty into it, it's astonishingly non-standard. And I'm going to argue that a universal language has 5 core elements: state variables, decision variables, I'll call it exogenous information, and then 2 functions, the transition function and objective function. I'm going to walk through each of these and then actually illustrate them in an energy problem. So state variables. This is oddly an area of tremendous confusion. If you go into the controls community, they'll use X as state, and they tend to often mean that state is a state of information. For example, you have a robot or a jet moving through the air, or a robot moving along the ground. What is its location? What's its current velocity? Knowing the state of the robot requires using sensors, and they will represent X as the state of that robot, and this community, especially in mechanical, electrical engineering, will understand that that's an information state. I'm going to say that probably most communities use S for state, and that's Markov decision processes, and computer science has picked up this notation as well, although the controls notation where X is the state has been leaking into these communities. Now, this is going to be my notation. So S is very standard notation for state. I'm going to break this up into 3 classes of variables. R for a resource state or physical state. What node in the network are you at? How much water is in the reservoir? I is, I'm just going to call it other information, such as what the weather is. And K is the state of knowledge. This is always a probability distribution. Now, you can view the classes of state variables as, here's a group of variables that we think of as a physical state. There's a larger class called information, which technically includes the physical state. What I like to do is, people tend to have sort of an idea of what the physical state is. In fact, I've run into many people who equate state with physical state. You know, I've seen papers written where they don't define the state variable, but they'll set up equations where they'll realize, okay, it's clear that they think of the state as the number of customers who's signed up for a clinical trial or the number of rooms that have been booked in a hotel, when in fact, there's also other information such as a weather report, but there can be this larger set of a belief state. What I like to do is to take the knowledge or belief state and just use that only for probability distributions. I like the notion of a physical state is simply very natural to people. And then I let I be any variable that we know perfectly, but we don't think of it as an information state. Mathematically, there really is no difference between R and I, but many of these problems, if you have a decision, it impacts R. Okay, that's not universally true, but that's often you're managing some resource. In learning problems, we are actively managing the state of knowledge. I may run an experiment and learn something, and that is impacted in the state of knowledge. Just a hint into one of the things that I've had to deal with is, I would love to challenge anybody on this session to see if you can go find an actual definition of a state variable. When you go to the operations research community, Bellman's classic text says we have a physical system characterized by any stage by a small set of parameters, the state variables. That's his definition. And he has the italics to say that's where he's defining it. You know, 40 years later, 50 years later, Putterman has a classic book, highly regarded, widely used, by the way, quite visible in computer science. It does almost the same thing. At each decision epoch, the system occupies a state. And Wikipedia says a state variable is one of a set of variables that are used to describe the mathematical state of a dynamical system. I get a little confused because I thought somewhere in grade school we learned that you're not supposed to use the variable you're defining in the definition. So I could go on and on. I finally have sat down and worked up my own, I'll call them definitions. I have two classes of definitions. One is that if you fix the policy, a state variable is the minimally dimensioned function of history, that if you combine it with exogenous information and a policy, it is the information that's necessary and sufficient to compute three functions: the decision function or the policy, the transition function, and the cost or contribution function. Now, a second definition is for an optimization problem. The first one is specifically for a sequential problem where you're given the policy. The second one is for a general optimization problem where you're searching for the optimal policy. And here I'm going to call it the information that's necessary and sufficient to compute the cost or contribution function, the constraints, and the transition function. Okay? Why is this important? Because later we're going to be really focusing on modeling and designing policies. And if you can't understand a state variable, you're going to have a lot of trouble. But these definitions, which I've been chatting about for a number of years now, and I've talked with many people, so far nobody has said, gee, you're wrong. But I have had people sort of say, well, I like this other definition. And I have to admit, what I like about my definitions is I can teach them, and I can teach them to undergrads. And I'm going to do a little exercise later that illustrates actually using the state variable. But I will close by noting that all properly modeled problems are Markovian. And that actually is something that not everybody agrees with. And I will politely say I think they're wrong. If you tell me that you have a problem that's not Markov, I will tell you that you have a problem where you haven't defined the state variable properly. Okay, so moving past that, decisions. Now here's another thing. Often when people describe a problem to me, I often find myself saying, what's the decision? Now in literature, there's three classic notations for decisions. In computer science, and some people in operations research, you'll see a lot of A for action, usually means a discrete action. Left, right, red, green, blue. In control theory, they like to use U, which almost always means a continuous vector, low dimensional, you know, maybe 2 or 3 dimensions, maybe up to 10 dimensions, but 10 dimensions is a lot. In the operations research community, we love to use X. That's the language of math programming. And if you don't have at least 10,000 dimensions, then you're just solving a toy problem. Of course, we have a lot of structure. Now, I'm not going to talk about yet how to make a decision, but I'm going to assume that we have some policy. We'll talk about this later. If you like X for your decision, I will take a capital X, put a superscript pi there. It depends on your state, and that's your policy. And we'll talk later about how to come up with these policies. But just take whatever variable, make it a capital, put the letter pi. Computer scientists, and by the way, other people in operations research, they like to use pi for policy. I like to use the letter pi not for the function, but for the information that tells you what type of function it is. I'll illustrate why that's important later. Decisions. Now, let's understand that decisions can come in a number of styles. Binary, such as stopping problems. Finite sets, you know, 1 through m, where m might be 100. Continuous scalars, continuous vectors, discrete vectors, or even categorical, okay? So in other words, these can be very low dimensional or very high dimensional. And we don't want to lock ourselves into modeling and solution methods that's limited to one class of decision. Exogenous information. Now here's something where there really is not standard notation. With the possible exception of the controls community that likes to use little w, I spent a long time talking to my stochastic colleagues, settled in on capital W sub t. Now, when you go to model a real problem, you know, you can have a generic variable like W, but I may have random waterfall and random demands and random prices. And I like to use notation that reflects the specific item that I'm modeling. But I have found I really like to know which variables are determined exogenously. I use this hat notation. And if you see in R hat sub t, what it means is this is a variable that is first becomes known at time t from outside the system, either from a probability distribution or from an observation. When you use this notation on more, you know, realistic, complex problems, it really cleans things up. One bit of notation that I really stick to is that any variable indexed by t is known at time t. And that sounds almost obvious, but oddly enough, the controls community does not use that style. They'll use little w to t that's random at time t. Okay, that's what they do. I think this is better. The transition function. So oddly enough, this is a concept widely used in engineering controls, not used at all in operations research, and I generally don't see it in computer sciences either. These are equations that say, give me a state, give me a decision, x, now give me new information that wasn't known at time t, and this function will take me to the state at time t plus 1. So you're supposed to have an equation for every state variable. This is widely used, which is one reason why in the literature it goes under so many different names. It's somewhat odd that in some communities, like operations research, my home community, and computer science, you don't actually see transition functions. Computer scientists, and by the way, many in engineering, like to work on problems where this equation is not known, and they'll call that model-free dynamic programming. The objective function. Okay, this is where things get really tricky, because in stochastic dynamic problems, objective functions come in many flavors. The dimensions of objective functions, you can have performance metrics, you can have properties like convexity and monotonicity. I'm not going to talk very much of this notion of final reward versus cumulative reward, but there's a lot of adaptive learning problems where I have to learn in the field, and if I do badly, I have to suffer the consequences, but I might be in the lab where all I care about is the final design. You can have functions that are easy to compute and hard to compute. I might need a field experiment. And when you have uncertainty, you have to talk about whether you're going to do expectations or risk measures. Performance metrics come in many flavors. Okay, I'm not going to read all these. These are all the different words that different communities use that I've run across. Objective functions can be written different ways. Linear ones for linear programming. You can have what I call state-independent functions where the function is not a function of the state. The decisions are, but not the function. And then you can have state-dependent functions, which is fairly common in computer science, where we write the cost or contribution or reward or gain or whatever you're using as a function of a state and an action and possibly the new information or possibly the downstream state. So far, this is everything I've ever seen in the literature. Characteristics of the problem, analytic behavior, computational costs, startup or switching costs, risk operators. This just sort of peeks at all the richness of different ways of formulating stochastic dynamic problems. This is sort of the circle of stochastic optimization. This function at the top, I've had people call this the fundamental stochastic optimization problem. Now, if you go to all these various problems, and I'm not going to go into these in any detail, you can actually come up with objective functions in a lot of different flavors. Notice that they evolve from maximizing over X to maximizing over policies. And eventually you end up with what I call sort of the ultimate or the universal objective function. This universal objective function, I have found I can model everything, okay? By tweaking the notation properly, I can take that slide of 15 books, take every single problem in any of those books, and model it this way. We have a cost or contribution function that depends on a state, although it doesn't have to. It depends on a decision where we're going to use a policy to say, okay, given a state, here's the action I will take. There's the new information. I have to take an average over everything that's random. And this is going to depend on an initial state, which can be deterministic information or Bayesian prior. So there can be probability distributions in this initial state. And then the hard part is this searching over policies. Okay, so this is what people have to get used to, and I'm going to spend some time addressing this problem of, okay, how do we search over policies? Let me give a little example from energy storage, okay? So here's a little tiny problem, and I'm just going to walk through how to model this problem. And I'm going to click off each of the elements of state, action, information, transition, objective. So when I sat down to do this, I looked at all the 5 elements and said, okay, let me write out the state variable. The first thing I realized is, wow, I don't know how to do the state variable until I've done the rest of the model. So we're going to do it that way. We're going to do the state variable last. But as I walk through all the steps, I'm going to put a red box around any information that we need. That's going to be the information that will eventually go into the state variable. So here's decision variables. Now what I like to do is, each of those blue lines is the decision to flow energy between 2 points. We can have constraints, and those constraints that include how much energy is being generated, what's the current load from the building, and R is how much energy is in the battery. I need to know those variables at time t. They form my constraints, so this is information I need. Now, exogenous information is new information coming from outside the system. Okay, so here I am being given information. This isn't dependent on any information I know now. The transition function, I have a series of equations, and each one of these equations depends on certain variables, which is information I need. Notice that the price of energy at time t plus 1 depends on the price at time t, and the price at time t minus 1, and the price at time t minus 2, okay? The objective function depends on a price that's random. It's known at time t, but as I go from t to t plus 1, and I'm also depending on a forecast where, because of that expectation, I will need access to the forecasts. I realize I'm going quickly, but let's pull it all together. So I have a cost function, I have the constraints for my decisions, I have a forecast, and I have, in addition to the constraints where I have to know E, L, and R, I also need to know those prices. Let's go ahead and create a state variable. Done. That's a state variable. It's all the information you need to step from t to t plus 1. Okay, all you do is look at all the equations and just pull together the information that you need. If you give me that list of variables, I'm ready to go. Now, oddly enough, this is not widely accepted. I'll have people who, first of all, people look at that and say, oh, that's way too big. I don't care how big it is. Don't tell me how big it is. I mean, they'll say, oh, that's too big of a state space. I don't care. This is the proper state variable. Some people will object to the pt minus 1 and pt minus 2. They'll say, that's not the state, that's history. I'm sorry, that's just what I call ugly thinking. Just because it became known in the past, it's still known now. Now, I don't need pt minus 3. Why don't I put that in the state variable? Well, because I want it to be minimally dimensioned. So this is the information and only the information I need to move forward in time. Okay? All right, we covered a lot there. I swam upstream of some very conventional modeling styles. I have had more conversations on this than I care to admit, but I think I've got this worked out. And by the way, all properly modeled problems are Markovian. Okay, again, that's running upstream of some pretty established thinking. So there is a common misunderstanding that state variables have to be simple. They don't. There's a tendency to refer to problems that depend on prior information as history dependent. I think that's just muddy thinking. Everything's Markovian. I don't care how long ago it became known. But let me just emphasize how important it is to understand state variables. Now, let's talk a little bit about modeling uncertainty before we get to policies. Modeling uncertainty. There's two ways uncertainty can enter this system. So the two information processes that drive the decisions that drive our process is decisions and exogenous information. The exogenous information comes from two sources. One is the initial state, and one is the exogenous information process. So to model, we need a system model, we need the initial state, and then the exogenous information process, and we need the cost of contribution function, by the way, along with the constraints. So the initial state contains anything deterministic and any state of knowledge, like a Bayesian prior, okay? Now, that's only for the initial state. Once we go to later states, we no longer include any information that does not change over time. Those are called latent variables. We simply take anything that's static and deterministic, and we leave it out of the dynamic state variable. Now, types of uncertainty. I finally, a year ago, sat down and started going back all the projects I had done and says, what are all the different types of uncertainty? I'm going to go kind of quickly here. I just want to highlight that uncertainty comes in a number of different forms. Observational uncertainty, so what's the CO2 content in the atmosphere? I don't actually really know. What's the inventory of oil? Prognostic uncertainty, that's the typical thing of forecasts where I have uncertainty in my forecast. If I run an experiment, I can have experimental noise. And as I go from t to t+1, if I'm running my robot around, I may have deterministic equations to tell me where the robot should be, but then there's other exogenous factors that may push it off course. Inferential uncertainty, this is where I try to infer certain parameters, but because of noisy data, I'm going to have uncertainty in my estimates of the parameters. One of the hardest is model uncertainty, where I admit I don't know the model, okay? And it can be the structure of the model, or it can be parameters for a given model structure. Exogenous uncertainty, you can have, the W process can have a baseline, high frequency noise and low frequency noise. Okay, so I can have oil prices are moving around, you know, day to day, but they are following long-term trends, which are also uncertain if I'm making long-term decisions. Control uncertainty. Boy, this was a new one for me. It took me a long time before I realized that when you make a decision X, or whatever notation you like, what actually gets implemented may not be what you decided. We ran into algorithmic uncertainty in one of our energy projects where there was noise in the algorithm itself, and that actually caused us problems when we were modeling wind and solar. Now, let me just briefly mention that we have Bayesian views of uncertainty and frequentist views of uncertainty. I can't get into this in this short presentation. I just want to mention that they're both very important, both relevant. I know that some people like to say that there's a big battle between Bayesians and frequentists. I think that's a lot of silliness. There is natural sources of uncertainty that's best represented as Bayesian. There's other sources of uncertainty that are best represented as frequentist. Types of probability distributions. You know, we tend to think that uncertainty can always be modeled as a normal distribution, but in fact, uncertainty comes in a wide range of forms, from the classical exponential families to heavy-tailed spikes, bursts, and rare events, okay? In the power sector, they always have to have a generator up and running, enough spare generation in case any one generator goes out, the biggest generator. So if the biggest generator is a nuclear generator, you're going to have 1.3 gigawatts of reserve in case that nuclear generator goes out. They don't have probabilities, they simply have a contingency. So I'm going to now be talking about policies. I and many others have been guilty for a long time where we focus all of our energies, if you're a stochastic optimization person, of coming up with good policies. And what we really did is we sort of faked our model of uncertainty. We didn't put too much effort into it. What we're finding is that the model of uncertainty is extremely important. In fact, I'm going to argue more important than coming up with optimal policies, okay? So the idea of designing optimal policies or good policies is good, but you can't come up with an optimal policy if you don't have a good model of the problem. And when we work on actual real applications, we tend to spend more time on modeling the problem than we do of coming up with good policies. That said, let's go design some policies. Now, when you look at those 15 books that I described earlier in the talk, it's amazing how many of those books really differ in terms of the class of policy, okay? First of all, let's get an understanding of what we mean by a policy. A policy is a mapping of a state to an action, any mapping. And I emphasize any mapping because I run into communities where they'll say, oh, I'm not doing a policy because I'm solving this very hard optimization problem. Yes, but they're still giving me an action from a state, so therefore it's a policy. Now, the hard thing is when we search over policies, we don't know how to do that. We know how to search over X. You know, we understand math programming and we can search over high-dimensional X. We don't really have tools to search over arbitrary spaces of functions. It turns out that a good hint is to go to those 15 books and say, well, what are they doing? Now, I have this very cute little slide here I wanted to share just to communicate that the notion of a policy is ingrained in the English language or any language. And every one of these rules represents in some setting a policy, the notion of a policy. So policies are basically rules for making decisions or guiding the decisions. It turns out that if you go to my slide with all 15 books, there's two fundamental strategies for coming up with a policy. It's exactly two. One called policy search, where I'm searching over some class of functions. And let's say I'm maximizing. And let's also pretend I'm using an expectation because I may not be. And I'm going to come up with a class of functions I'm going to search within the class. We're going to call that policy search. And the other is policies based on lookahead approximations, where I'm going to make a decision now that'll, I'll be in a state, I'm going to make a decision that will take me to a downstream state, and then I'm going to think about what happens downstream. And I would like to approximate that, and if I can do a good approximation, I'm going to maximize that and call that a policy. Let's drill in a little bit more detail. Policy search, it turns out, you can further divide into two key classes. One is some kind of analytic function that if you give me a state, I'll give you an action. Okay? It can be a neural network. It can be a rule. It can be a lookup table. It can be a linear model. Okay? A lot of people in computer science, to some extent people in operations research, when they use the word policy, this is what they mean. I decided it needed its own name, so I've come up with the term policy function approximation. Okay? Now, so the second category, look at that category 1B. This is something you'll never see in the literature. This is a policy where we're going to maximize some modified cost function. I've never seen this in the academic literature. It's widely done in professional practice, and I'll illustrate later. Okay? This is one of the ideas that I said, okay, this is what industry really likes to do. It turns out that what they're doing is quite good. It works well. And what it needs is a fancy name and fancy math. So this is a case where by standing back and looking at it in this way, I came up with an entire class of policy that had previously been undiscovered. So this is policy search. Now, generally with policy search, whether you're working with PFAs or the CFAs, you have to search within a class of functions. Okay? Now let's go to the look ahead. So this is a really frightening equation. I want to sit in a state S, take an action X, or in computer science would be action A. Now I have an ugly E and a max over policies and another E, and this looks hopelessly frightening. So obviously, we can't actually compute this. So one way to handle it is to boil this whole big messy function down into something called a value function. And people like to call this dynamic programming. So when people talk about Bellman's equation, this is what they're talking about. If they're doing Q learning, this is what they're doing, okay? This is not the only way to do it. Just like with the policy search, there's two core categories. 2A comes up with some sort of function, a value function. The other is what we're going to do is, see all those tildes? So the problem with this first equation is it's just way too complicated. Even on fairly simple problems, you just can't compute this. So, but the other thing that we can do, and we do a lot of, is we're going to say, you know what, let's going to simplify the problem. And I'm going to actually walk through specific illustrations of each one. So policies based on value function approximations, this is the foundation of everything that talks about Bellman or Hamilton-Jacobi optimality equations. Exact value functions are rare. They're possible in certain cases, but generally rare. Approximate value functions are generally based on certain algorithmic strategies. Okay, and once again, depending if you had any background, like in reinforcement learning, this is what you've been doing. Now, the ultimate look-ahead policy, if we could compute it, is optimal, but I cannot compute this expectations. I cannot maximize over policies. I can't actually do this. So we replace it with all these tildes. What we're doing here is we're changing the problem. Instead of optimizing over the future in terms of the real problem, I'm going to optimize over the future in terms of some modified problem, something that's easier to solve. So we have to approximate. There's different ways to look ahead. So one is a one-step look ahead, and there are problems where a one-step look ahead works extremely well. This tends to be true in what are called learning problems that don't have a physical state. Otherwise, multi-step look ahead, so every time you use Google to plan your path to a destination, you're doing a multi-step look ahead. You're taking a highly stochastic problem, modeling it as a deterministic problem, solving it deterministically and saying, this is what I'm going to do. So we often use these multi-step look aheads. Now, between what I've just described as 4 classes of policies, 2 based on policy search, 2 based on look-ahead models. So I call the first 2 PFAs and CFAs, policy function approximations and cost function approximations. These are the ones where there's some tunable parameter and I have to do policy search. The second 2 are based on some way of approximating the future, either through a value function or a direct look-ahead. We have just covered all 15 books. Now, of these 4 classes of policies, 3 of them require some type of machine learning. So I like to warn my students that if they want to come work with me and do optimization, they're going to be doing a lot of machine learning. Okay, so there's a lot of statistics. The direct look-aheads avoid any machine learning, but they pay for it. Okay, and sometimes you have to do it. Sometimes I tend to think of the direct look-aheads as what you do when all else fails. The problem is all else often fails. So this is a very powerful set of strategies. The first of these is a deterministic look-ahead. Then there's other ways of putting uncertainty in the look-ahead. Those get very complicated. So you're going to be doing some type of approximation. You can do lookup tables. You can do linear parametric models, nonlinear parametric models, non-parametric models. You're going to have to learn some statistics. Okay, I've spoken to people who clearly they didn't have a strong statistics background. You're going to have to get a pretty decent statistics background. So what do we end up doing? So to find the best policy, we have these 4, let me call them meta classes, the PFAs, CFAs, VFAs, and it should be DLAs, the direct look-aheads. And then for each one of these classes, there's subclasses, and somewhere you end up with a bunch of tunable parameters that you have to tune. Okay, so once you've picked a class of policy and a class of function within the class, then you end up with some tunable parameters, and then you have to find some way to search over those parameters. Okay, this is the grand vision of how to search over policies, and it's very practical because this is what everybody's doing. Let me skip past this. Now, what I'm going to do here is I'm going to talk through the 4 classes of policies. I'm going to give you very quickly some actual applications, very quickly. PFAs. Here's a simple PFA. I'm in an energy setting. I have a battery by Convergent Energy and Power, a new company here in New Jersey. I have highly stochastic electricity prices. What I'm going to do is I'm going to store energy when the prices go below a number. I'm going to sell back to the grid when the price goes above a certain number. The question is, how do you put these two numbers? Okay, so the policy is a simple function. You know, we charge when the price is below a lower limit, we discharge when above a limit, in between we do nothing, and down below is an actual graphic showing the energy in the battery, and we see that we sell it into the grid every time the price comes up. Now I have to tune over those thetas. How do I do that? Well, I'm going to max over the thetas, this expectation, so I can't compute the expectation. So here's what I'm going to do. I'm going to fix the lower theta, I'm going to fix the upper theta, then I'm going to go into a simulator or possibly the real world. And now I'm going to get a noisy observation of that function. Now we have algorithms that, given that noisy observation, we can optimize theta. This is why people like me get so excited, because I love to design these algorithms. And by the way, there's anybody who likes algorithmic research, this is not something for which there's standard go-to algorithms. There's a whole host of algorithms that you can go to, and I would consider this still, after all these years, very active research. A CFA. So here's actually how I discovered CFAs. Was working with an independent system operator. So these are the grid operators that have to plan which generators will be used to generate energy. Now, what they basically do is they sit at, well, let's say noon on one day. Now, the generators are mainly steam and gas turbine. Now, steam can be, well, it could be coal or nuclear. Increasingly, it's natural gas. But steam involves boiling water. You have to plan it a day in advance. The gas turbines, you have to plan 30 minutes in advance. So I have decisions X that have to be made a day in advance, and other decisions Y that have to be made an hour in advance. Now we can solve this deterministic problem, but buried in there is I'm using stochastic forecasts. So we can call this a policy. This would be a deterministic look-ahead policy. And a lot of people like to say, oh, those grid operators use deterministic models, and that's just simply false. Nobody uses this model. They use something like this. What they do is they solve a deterministic problem, but it's modified. And what they've done is they've got a couple tunable parameters that say, look, because my renewable energy might drop below, I have to have reserves. And by the way, if the wind spikes, I'd like to have some extra storage that I can store that excess wind. So I have these two tunable parameters. All right, now I'm back to having two tunable parameters buried in my policy. Now, here's an actual simulation, and those sort of reddish circles are highlighting places where we had an outage. Now that sort of reddish color, that's the gas turbines. And what we really like to do is to run more gas turbines in background, because that's how we're going to get the red out. Now, what we're going to do is we're going to go in and impose that I want a certain amount of gas turbine reserve. And when I do that, I now have gas turbine reserves all the time, and we got all the red out. So now I've designed a robust policy. By the way, this is what's done in industry. And academics love to criticize it because they like to call this policy a deterministic model. It's not. It's a modified deterministic look ahead tuned in a stochastic real-world setting. This is stochastic optimization. People don't understand that just because you're solving a deterministic model, you're still doing stochastic optimization. The nice thing is that by imposing these reserves, you have a lot of control over the structure. That's why we call it a parametric cost function approximation. Value function approximations. Now, I love to use VFAs when I'm doing my energy storage problems. Here's my favorite pet energy storage problem. I have 4 dynamic equations. So I have a 4-dimensional state variable. 3 of them evolve exogenously. 1 I control, which is the energy in that battery in the middle, that poor little battery. We like to solve Bellman's optimality equation, but the state variable has 4 dimensions, the decision variable has 5 dimensions, the exogenous information has 3 dimensions. I got to tell you, you cannot put this in a dynamic programming code and solve it. It just won't work. But what we can do is we can approximate the value function. So if we have energy held over, I can either use it now or hold it for the future. The value of holding it for the future is captured by the value function approximation. We have iterative algorithms for coming up with these value function approximations. Let's imagine I have batteries spread all around the grid, and for each one, I have a value of storing energy in the grid at each point in time. Now, the way we learn these value functions is what we're going to do is we're going to set up an animation where we're going to step forward in time using whatever value function. Maybe we'll just start with 0. And we're going to do these simulations over and over and over again. We might do it 100 times. And over the 100 iterations, we will steadily learn these value functions. And then over the iterations, our results generally tend to increase, but not uniformly. This is the nature of adaptive learning. Here's a grid where those sort of angry red rectangles is where there's very high congestion. After we allow the batteries to be optimized, we can really get a lot of the congestion out. So this is highly scalable, works very well. This is a great application of using value functions. Finally, we have the good old direct look-ahead policies. So I like to illustrate a look-ahead policy with the way I play chess, which is when I move my bishop, I put my finger on it and I think about what I'm going to do next. If you're in Google Maps, you're going to allow it to plan a path to the destination. That doesn't mean you're going to follow the path. That's just going to get me started. This is a direct look ahead. A decision tree is a different form of direct look ahead with uncertainty in it. Okay? Typically, most direct look aheads look ahead deterministically, but you don't have to. You can look ahead stochastically. Usually these things blow up. Now, the key thing with a look ahead model is that you don't want to confuse the look ahead model with the base model. You have to keep in mind that the problem is to come up with a policy. The policy may be based on solving an approximation of the future. There is almost universal confusion about this in the academic literature, and it's almost universal. It's very hard to find a paper that uses a look-ahead model that properly distinguishes between the look-ahead model and the base model. Now, when you do a look-ahead model, there's various types of approximations that you're going to use. Horizon truncation, stage aggregation, outcome aggregation, that's the uncertainty. Discretization, you can do all kinds of discretization. And there's something called dimensionality reduction, which is basically fancy words for saying, I'm going to leave some variables out of the look-ahead model that I am going to capture in the base model, okay? And I can give different examples of that. So a look-ahead model, the term look-ahead model is used in the literature, not very much, not very much. You will find it. The term base model is mine, and I spoke to a number of my colleagues in the research community about this word base model. I'll be honest, I'm not in love with the word. I can't find a better one. I have certain colleagues who say, oh, you should call it the true model, and there's reasons why I don't think that's going to be a good solution. There's a lot of opportunities to do a deterministic look-ahead model to solve a stochastic problem. And as I pointed out earlier, you can do a modified deterministic look-ahead that has to be tuned in a stochastic base model. Now, so I really struggle with notation. So one of the ways that I say, look, I've got to have notation for the look-ahead model so it's not confused with the base model. So I created this tilde notation where I take all the notation of the base model and I use it for the look-ahead, but I put tildes on top, and I also put everything with a double time index. So the first time index t is where you are in the base model, and the t prime, the second time index, is where you are in the look-ahead model. So to illustrate, if we have our look-ahead model, we have all those tildes representing, and notice that I now have s tilde, and everything has a double time index. What we're now doing is we're solving an approximate problem in the future. So my policies can be limited, my expectation can be limited, my state variables can be simplified, my decisions can be simplified, and my horizon is truncated. So there's all kinds of neat approximations that then have to be tested in a simulator. So the simplest type of Lookahead model is deterministic. No expectations, no uncertainty, no even hint of what a policy is. It's just a deterministic optimization problem. That lower one, this is what people call stochastic programming, where you say, oh, I'm going to have a set of scenarios that might happen in the future. And now you have a deterministic lookahead, but instead of one deterministic lookahead, you may have 20, and you have to solve them all at the same time. Now, this is an image I really like. So here is our lookahead model where I'm peeking forward. I solve the problem, figure out what to do now, roll forward, do it again, roll forward, do it again. This image distinguishes between the real problem, I'll call it the base model, and the look-ahead model. Okay, I really love this image because it just captures what it is that's going on. Now you can look ahead stochastically. Now looking ahead stochastically, you almost always end up blowing up. And usually these scenario trees, as they call them, end up being very large. But in theory, you can do this. And you can look ahead. Generally, that's a very hard problem. Solve it, roll forward, solve it, roll forward. It's quite rare to find people who actually do these simulations, but there are people who do it. It's quite rare. However, I do have a lot of confusion in this community because they'll solve these stochastic lookahead models because it's so hard to solve that once they do solve it, they say, yes, we're optimal. And I have to say, yes, but it's not an optimal policy. And I've had people outright, flat out disagree with me. And I'm sorry, they're wrong. That's just not an argument that people can defend. A stochastic look-ahead model is hard to solve, but when you're done, it's still not optimal. Now, let's take up my little energy storage problem and illustrate our policies. I'm going to create 5 problems. And what I've done is I've tailored the problem for each class of policy. Okay, I'm not going to go through the details. I have a paper on this that's been published. The first 4 are really tuned for each of the 4 major classes of policies, and we really worked on the 5th one to come up with something that was ideal for a hybrid. Then we had designed 5 policies, the 4 pure policies and a hybrid. By the way, you can mix and match. And this is the work of Stefan Meisel, a former postdoc. He's now teaching in Germany. And what we did is we designed it so that for each of the 5 problems, each of the 5 policies is optimal on one of the classes of problems. In other words, the highlight says, yes, you have to be aware that all of the policies need to be in your toolbox. Whereas individual people, like I spent, I don't know, maybe 20 years of my life on VFAs and wrote a book thinking I could solve every problem with VFAs. There's a whole community in computer science that does policy search, and those are PFAs. Deterministic look ahead, there is an entire world, books, on what is called model predictive control. What that means is deterministic look ahead. People have spent their careers on model predictive control. We've created a simple little problem where everything can be made to work best. So, closing remarks. Okay, I'm a minute away. The transition from deterministic optimization to stochastic optimization it's not as hard as people think. This first slide sort of illustrates, up top is a deterministic problem, nice linear program. The second bullet says, what if you want to make it stochastic? And I'd like everybody to look at that equation to see how easy it was. Every time there was an xt in the deterministic problem, I replaced it with a policy. Okay? And those equations that link over time have to be handled by your transition function. Writing the problem correctly is not hard. All right? It's a simple, write it out deterministically, and then every time you see a deterministic x, put in your policy, depends on a state. The state evolves over time. This is mathematically correct. Now you have to search over policies. I like this problem because on the deterministic, on the left-hand side, this is the way people will write a deterministic problem. On the right-hand side, I'm like, and now here's how you do it for a stochastic problem. So the deterministic problem, we're optimizing over X, and the stochastic, we're optimizing over policies. The constraints at time t, in a deterministic problem, we don't distinguish between constraints at time t or over time, but in a stochastic world, they're quite different. You have to clearly differentiate. The policy has to be designed to obey constraints at time t, and the transition function is what links things across time. When I go from stochastic to deterministic, in stochastic problems, I spend most of my time modeling. In deterministic problems, modeling isn't really that big a deal, okay? Algorithms are the big deal for deterministic. For stochastic, searching for policies is sort of the analogy, but searching, you know, by the way, optimal policies are extremely rare. Generally, what you're looking for is good policies, and on any real-world problem, what you really want to do is find a good policy, you know, a pretty good policy, and then switch to modeling the uncertainty, modeling the problem, but especially the uncertainty, because that's actually more important than an optimal policy. You'll get this over and over again. Deterministic people don't have to worry about that. And by the way, evaluating a policy is hard, okay? Sorry, you have to set up simulators. You have to think about whether you're going to do expectations or risk measures. Deterministic people have that easy. Oh, just add up the costs. So this is the big transition. I will close with this slide that in effect says, look, in one slide, this is how you write a sequential decision problem. Okay, this covers every one of those books I showed you. Then you look for policies, then you model the uncertainty, and I think this will clean up a lot of problems. This is the image that I like the most that says to get from theory to applications, in between is computation and modeling. And boy, would I love to see people spend a little bit more time on modeling. And I'm done. I know that's a lot to absorb. The real challenge, and Carla, let me tell you what I would love to do at the next ComStus meeting. To have a modeling session, a live modeling session with a whiteboard, no PowerPoint. Have people come with a handful of previously vetted problems, and then we will sit and do live modeling to say, okay, here's how we would model your problem. And I think this would be a great exercise. It would utterly clean up so many papers.
Yeah.
We did have one question that came in earlier in the talk.
I heard a blip, but then I didn't see the chat box.
Yeah, it came in the Q&A from an anonymous viewer. You mentioned that all well-formulated problems are Markovian. What if it is too impractical to include all the necessary variables to make the problem Markovian, and the problem can still be solved without the Markov property?
All right, I don't know how to model the problem if you haven't modeled it correctly. Like, for example, let's fix a policy. See, this is the problem, is people who are jumping to policies. Let's fix the policy, whether you think it's optimal or not. How do you evaluate the policy? You have to simulate it. To simulate it, you need a proper model with a proper state variable. I don't know how to do that without a proper state variable. And if it's not Markovian, you don't have a proper state variable. It means you can't simulate a policy.
Okay.
Well, this is Tom Dietrich. Can you hear me?
Yep, Tom.
Yeah, just checking my microphone. So sometimes we have simulators that have a bunch of internal state variables that we can't get access to. So in reinforcement learning, often that means, for instance, we can only simulate along complete trajectories because we don't really know what's going on inside. We can't jump to a specific place in time and space. So I think that's one of the examples of where people say, well, maybe I might still be able to do some kind of policy search, right? I mean, their policy search works with POMDPs even without modeling the information state or the knowledge state. So I don't need to pull out the Markov. to solve the problem.
Are you able to simulate the policy?
Yes.
Okay. How are you simulating the policy without, in other words, is this sort of a black?
I can simulate the policy, but I cannot simulate the transitions explicitly. I just have this computer program, I hand it a policy, and it simulates full trajectories.
Okay, fair enough. So in other words, the simulator is available.
Right.
Even if it's black box. So for example, by the way, one way to evaluate policies is in the real world.
Yes.
Where I don't have access to a model at all. I can just, you know, a lot of Q learning is motivated by this setting.
Right.
So I can put in place a policy and then follow it in the real world. I have no clue what the transition function is. I'm just observing state transitions. That's fine.
Mm-hmm.
And by the way, a great, interesting challenge for policy search is doing online policy search.
Yeah, yeah. One other question, which is just my own ignorance. So, so model predictive control. I didn't realize that people assume a deterministic look-ahead policy in those cases.
The controls people do.
Okay.
Okay. It's funny because if you interpret the term model predicted control, obviously model predicted control can be a stochastic model.
Right. Yeah.
But if you open up a book from the controls community, and so in my career of talking to people from many areas, I had a controls expert in my lab years ago who basically said, look, Warren, controls is deterministic. And if you go to the controls community and you see a book on stochastic controls, usually it's written by and for mathematicians. If you have an actual engineering book, it's usually deterministic. So they will sit there and just assume that, well, of course, you have to look ahead deterministically because your fundamental problem is deterministic.
Right.
So, but I talk to many people who just, when they say MPC, they mean deterministic look ahead, but not everyone.
Right. Whereas in the reinforcement learning literature, we talk about doing some fixed amount of look ahead with whatever model we have. And some people have said, well, that's the same as model predictive control, so maybe we should borrow that word. But you're saying borrowing that word might confuse people as much as it would enlighten.
I'll be honest, it doesn't confuse me, and I don't object to it. I'm not somebody who wants to equate MPC with deterministic.
Okay.
I'm not in that camp. To me, model means model. So if your model is stochastic, well, then that's what your model is.
Right.
Okay.
So, and in the deterministic case, then the only way that the actual stochasticity of the world enters is that at each time step, we observe the realizations of all of the exogenous variables.
Sure. Possibly just in terms of knowing the updated state.
Right, yeah. Mm-hmm.
You know, it's funny. The first person I ever saw using the term MPC, but solving a stochastic look-ahead was somebody from computer science.
Okay.
The OR community does
They were
not,
trying.
the operations research community doesn't use these words at all. You know, we call it rolling horizon procedures. But when you say rolling horizon procedure, almost always it means deterministic. So there's this whole community in stochastic programming where they do stochastic look ahead. And it's very funny with that community. They're very defensive. They're very proud of what they do. And if you try to call it a policy or even a rolling horizon procedure, they get quite insulted.
Okay, well.
The problem is they're wrong. You know, it's like, I'm sorry, you're just wrong. But, you know, it's very funny to get these people and realize how they think. And it's, you know, to me, I'm really trying to use standard thinking as much as possible. It's just that at the end of the day, if it is a policy, it just is, and you can't change it. And if it's not an optimal policy, you can't just pretend it's optimal. Just the notion that what a lot of people are doing is coming up with a policy, and then they don't understand that that's fine. There's nothing wrong with that. And there's nothing wrong with whatever method they have for coming up with a policy. But often they don't, and this is not true for everyone, but there are pocket communities where they don't understand that that policy is a possible solution to the objective function that I was showing you in my talk. This thing here. So that, can everybody see that screen? It's the one with the max over pi e of something. Is that showing?
Yes.
Okay, so that expectation, nobody can compute that expectation. So really what you're doing is a simulator, So everybody will say, well, of course you need to simulate the policy, without realizing that that is the objective function. It's kind of funny, but let me put it this way. I hope that before I retire, I can change the way people think. Now, the confusion here is not universal. Okay. By the way, anybody who really comes from a dynamic programming community, which, by the way, includes most of the reinforcement learning community. But Tom, for example, Monte Carlo tree search would be a lookahead. I think you would agree it's a lookahead. It's a stochastic lookahead.
Absolutely.
It's a stochastic lookahead.
Yeah.
I'd like to think that people who do Monte Carlo tree search understand that that is a lookahead policy. And it's a possible solution. What's that?
I think everybody does, but I don't know.
But so in operations research, they don't call it Monte Carlo tree search, they call it stochastic programming. It's not the same, because in Monte Carlo's tree search, the actions are discrete. In stochastic programming, the actions are vectors. And so stochastic programming problems are so hard, and people spend years and years just to solve these problems, that when you come along and say, congratulations on solving that problem, by the way, your optimal solution of your lookahead is not an optimal policy, they absolutely flip out.
Right.
It's just like, okay, thank God I'm older and I'm tenured.
Yeah. I mean, they've done essentially one step of policy improvement.
Yeah.
Yeah, which is a good thing.
Which is a good thing.
And doing that optimally is a good idea too, but yeah, okay. Well, thank you very much.
Now, one of the things that this has done for me is it's quite recent where I've sort of said, okay, optimal policies, with rare exceptions, are impossible. So really what we're looking for is good. And once you admit that you're looking for good, how can you have a good policy if you don't have a good model? I'm telling you, only in the last year or two did that really get into my head that says, oh gosh, I've spent a lifetime focusing on X. What I really need is to focus on W. Or maybe S naught. And that's been a real shift for me. That's a big mind bender for me. So the people who focus on uncertainty modeling, there's a whole community called uncertainty quantification. There's a whole journal by a SIAM on uncertainty quantification. These are people who do not do optimization. They only do stochastic modeling. They're mainly scientists. But I got to tell you, when I work on real problems, we're spending way more time modeling the uncertainty than we are coming up with an optimal policy. And that
excellent talk, and indeed, this is a jungle, and it's good that you are trying to, sort out all this terminology. I love your suggestion that we should have maybe, at the next meeting, the CompSust, some big session where you will model all our problems correctly. And so thank you so much for your talk, Warren. Our next talk is going to be on a Thursday, December 15th at the same time. So on Thursday, December 15th by Professor Daniel Sheldon. Daniel, do you have a title for your presentation or not yet?
Not quite yet.
Ah, okay. So, but I'm sure it's going to be good, and I'm sure you are going to model all this uncertainty properly. Let's thank again, Warren.
Thank you.
Bye-bye.
Okay, bye-bye. Thank you.
Bye-bye.